Next, we will introduce another key circuit component, the capacitor. Capacitors are devices specifically designed to store electric charge. They are used in many applications, like tuning the frequency of radios or as filters in power supplies. A capacitor is made of two conductors called plates. They are separated by an insulator. When the capacitor is charged, these plates carry charges of equal magnitude but opposite sign. This separation of charge creates a potential difference between the plates. The amount of charge Q a capacitor can carry is directly proportional to the potential difference, delta V. The constant of proportionality is the capacitance C. So we can write it as Q equals C times delta V. We define capacitance as the ratio of the charge on either conductor. So we can write C as Q divided by delta V. The SI unit of capacitance is a Faraday, or just F, named after Michael Faraday, where 1 Faraday equals 1 coulomb per volt. A Faraday is a very large unit, so typical capacitors are measured in microfarads or picofarads. A common design is a parallel plate capacitor. The electric field between its plates is very uniform near the center, but become non-uniform near the edges. A capacitor is charged by connecting its plates to a battery. The battery acts like an electron pump, moving electrons from one plate to the other. This creates a separation of charge on the plate. In this process, the chemical energy from the battery is converted into electric potential energy stored in the capacitor. For a parallel plate capacitor, the capacity depends on its geometry. It's directly proportional to the area of the plates and inversely proportional to the distance d between the plates. The constant epsilon 0 is the permittivity of the free space, which is given by this number. So this is the formula for the capacitance of a parallel plate capacitor.